Welcome to Physics 30 Prep Fast Track, Lesson 3-2. We're talking about circular motion again, this time caused by gravity rather than friction. So, in the previous lesson we equated friction with the centripetal force. We said that the force of friction was causing the centripetal force, therefore Fc was equal to Ff. In this case, when we talk about the planets, they're not held in their orbits by friction but by gravity. So we look at the orbits of satellites in this lesson, and since there is no significant friction, the only force keeping the planets in orbit is the gravitational force. And so the gravitational force, of course, is given by force of gravity is gm1 m2 over r squared, or sometimes if you're close to a planet and you know what g is, then you could say that it's just equal to mg. And of course centripetal force is equal to mv squared over r, or 4 pi squared rm over t squared. And since we're saying that the centripetal force is caused by gravity, then that means that the centripetal force is equal to gravity. When we assume the orbits of satellites are circular, they are really elliptical, we can use these relationships to solve for orbital period. The orbits of the planets are close to being circular. All right, so it works out fairly closely, and of course if you really want to get specific, then you have to bring into the equation that it's elliptical. It makes the mathematics a little more difficult. This is something Newton and Kepler discovered back in the 16th and 17th centuries. All right, so if you know that Fc is equal to Fg, then you can say that Fc, which of course is mv squared over r, is equal to mg. Or you can say the other formula for Fc, for centripetal force, is 4 pi squared rm is equal to mg. Or the other two combinations you could have is centripetal force here is equal to the other formula for gravity, or centripetal force here is equal to the other formula for gravity. So there are 4 different ways you can have the centripetal force equaling the gravitational force, and we'll look at a number of different examples of that. So example number 1, it says an asteroid orbits the sun at a distance of 3.7 times 10 to the 11 meters. The mass of the sun is 1.99 times 10 to the 30. What's the speed of the asteroid? Well, what's holding the asteroid in orbit? Well, the centripetal force is caused by gravity, therefore the centripetal force is equal to gravity. And of course you have to decide which centripetal force equation do I want to use. Well, I've got mv squared over r, or I've got 4 pi squared rm over t squared. Well, since we're asking for the speed, you should use the formula that has speed in it, and that's the only one. Now, which formula do I use for gravity? Well, there are 2. There's g is equal to gm1 m2 over r squared, or there's F is equal to mg. Well, we don't know what g is. We know what g is close to the Earth, it's 9.81. But what about out there where that asteroid is? We have no idea what g is, little g, so we have to use the formula gm1 m2 over r squared. We do a little bit of canceling. One of the r's cancels one of the r's. The m here cancels the m2 here, and we end up with v squared is equal to gm1 over r. That is g, the gravitational constant, times the m1. Now m1 is always the mass of the central object, not the mass of the object that's orbiting. And so what we end up with is, of course, v squared is equal to gm1. Remember that m1 is 1.99 times 10 to the 30, the mass of the sun, divided by r, that is how far is the asteroid from the sun. We get v squared is equal to a fairly large number. When we take the square root, we get 18,940 meters per second. That is very fast. And as a satellite gets closer to the sun, it actually moves faster. And the Earth, being closer than 3.7 times 10 to the 11 meters, it's only about 1.5 times 10 to the 11 meters, actually moves about 30,000 meters every second, or 30 kilometers per second. So there's a good example of the centripetal motion of a satellite, and you can use that relationship that the centripetal force is equal to and caused by the gravitational force. And one more example, it says an asteroid orbits the sun at a distance of 3.7 times 10 to the 11 meters. If the mass of the sun is 1.99 times 10 to the 30, what is the period or the time of one revolution of the asteroid? Remember, the period of the Earth around the sun is 1 year, or 365 and a quarter days. What is it for this asteroid? All right, so in this case, again, what's causing the asteroid to be in orbit around the sun? Gravity. So gravity is causing the centripetal force, so gravity is equal to the centripetal force. And this time, though, we're not interested in the speed, but we're interested in the period of rotation, the time it takes for the asteroid to go around the sun once. That's called the period. And of course, again, we don't know what little g is, so we have to use gm1 m2 over r squared. This is one of your more complicated derivations, but solving for t squared, you get 4 pi squared r cubed. All right, the r's don't cancel, they actually multiply. M times or divided by m gm1 m2. One of the m's cancels, the m2 cancels the m2 here. And then, of course, that gives you t squared. So this is t squared, and to find t, you take the square root of all that. And of course, what we get is the square root of 4 pi squared r cubed. And you can see the r cubed there, divided by gm1. You have to get a little practice with your calculator to get this. What you should get is 1.507 times 10 to the 16. Now that's t squared. When you take the square root of that, you should get 1.23 times 10 to the 8 seconds, which is, when you divide by how many seconds in an hour? Take this number, divide by 3,600. That's how many seconds in an hour. You'll get this many hours. Divide that by 24. You'll get 1,421 days. And of course, an Earth year is only 365 days. So that asteroid takes about 3.89 years, or our years, to go around the sun. Of course, it's only 1 year for it, because it takes that particular time to go around the Earth once. And of course, it's 3.89 of our years. And the speed increases as the satellite gets closer to the sun. And the period decreases. And of course, when we talk about Kepler's 3 laws, which we don't really do in this particular course, Kepler goes into this a little bit more. If you're interested, you can look at a few websites that deal with Kepler's 3 laws. Newton used Kepler's 3 laws to develop his gravitational law. And so these scientists, they build on each other's discoveries and announcements and arguments, and that's how Newton, without Kepler's help, he probably wouldn't have developed his ideas as quickly. All right? And that is circular motion due to gravity.